Hello everyone. Today in this video I have taken up another problem on network analysis. The problem reads this way. Selecting one and 4 ohm resistor as reference node, determine V1 such that the current through the 4 ohm resistor is 0. The method suggested for this problem is node voltage analysis. We have done already a problem on node voltage analysis, like I have already uploaded a video on node voltage analysis. This is another network analysis technique. Typically in this particular problem, he is asking a specific node to be taken as the reference node, and we are expected to find out the value of V1 such that a certain circuit condition is met. That is, the current through this 4 ohm resistor is made 0. When will this 4 ohm resistor not carry any current? That is the thing that we are expected to determine. So what is the value of this V1 such that there is no current in this particular branch of 4 ohms? And he has also asked you, in the problem it has also asked that 1 into 4 ohm resistor be taken as the reference node. This is another condition that we have in this particular problem. It is a simple problem. There is nothing very complex about it, but then it would give you an insight to the node voltage analysis, in the sense that irrespective of the reference node, one can always go about doing the circuit analysis. Let's see how we proceed with this particular problem. Here, as we can see in this particular problem, we have voltage sources, and it would be convenient, rather easy, if we can convert the voltage sources to their equivalent current sources and then proceed. That way it becomes little easier. Otherwise also you can continue having these voltage sources and one can proceed with node voltage analysis. However, I will for the ease of understanding, I will convert the voltage sources to current sources and take one end of 4 ohm resistor to be the reference node as suggested in the problem, and we will go ahead determining the magnitude of V1 such that there is no current through 4 ohm resistor. Alright, so let's try to convert the sources. Okay, I will write it down so that when you pause and read, you will understand. Converting the given voltage sources into their equivalent current sources. We can write the network as, we can rewrite the network as below. Okay, so what do I do is, I will try to convert this voltage source into its equivalent current source and this voltage source into equivalent current source. What would be the magnitude? The magnitude of the current source is simple. V1 volts and 6 ohm resistor will result in a current source. I will write it here, which will have a current source with its internal resistance to be 6 ohms put across it. This is how we try to convert. This is V divided by 6. It is simple Ohm's law. The current is equal to the voltage divided by the resistance. So many amperes. V divided by 6 amperes of current. This current source will pump in the direction of the arrow, and 6 ohms will come across the source. Similarly, we will convert the 50 volt source as well. Okay, so we will rewrite the network. I will erase this part and we will rewrite the network. So how will the network be? So what I do now is, I will try to copy this figure so that I'll save the time of rewriting the network. I'll paste it, but however I will have to do some adjustment. I'll do it quickly. And I'll remove the 6 ohm. So now this will become my current source, and here also I will I'll remove this 2 ohm resistance which will come across the source. This also I will have to replace it by a current source. I will take my white pencil back, I'll connect it back. This way I'll make it. So now the magnitude of this voltage source is this current source is V1 divided by 6. So many amperes of current. So I'll put the current source here. Okay. Similarly, the current source here will have a magnitude of, it is 50 at an angle 90. 50 at an angle 90. This is the magnitude of the voltage source divided by the resistance of 2 ohm. This will be the current. Or in other words, it is 25 at an angle 90 degrees. So many amperes of current. Okay. However, where is the internal resistance is going to appear? The internal resistance is going to appear across the current source. So 2 ohm resistance will come here and 6 ohm resistance will come here. So I'll take the same green pencil back, and this is 6 ohms. This is 2 ohms. Alright, so I have converted this into a current source. Now, additionally, he says in the problem that 1 and a 4 ohm has to be taken as the reference node. So I will take this node as the reference node. Okay, so if that node is taken as the reference node, how many nodes are left with? What am I left with? How many nodes are there? So if I can identify the nodes with a different color, perhaps I'll take this color. So there is one node that is formed here. This I will denote it as VA, the node A with a potential of VA, and the other node here is VB. These are the only 2 nodes we have. This entire thing, this, everything is VB, right? Alright? This thing is datum node. This entire thing is the datum node. It is the reference node. There is one more node VA. So this is VA, this is VA, this is VA. So apart from the reference node, we have 2 more nodes VA and VB. So we need to determine the potential of VA and VB. So how do we do? We will apply simple we will write the nodal equations by inspection. Alright. So how do we write the nodal equation? By inspection. The thing is simple. We have done elementary problem on nodal analysis. If you want, you can refer to the initial problem so that the writing of the equations can be understood. Okay, we will now write the equations by inspection. Okay, how do we write? Writing the nodal equations. I'll explain it once again. Okay, so we will try to write the nodal equation. We write equations at the node VA and another equation at node VB. Okay, so it is the sum of the admittances meeting at node A. So when we write a nodal equation for VA or for node A whose potential is VA, we try to take sum of the admittances meeting at node A. So sum of admittances 4 ohm is 1 and a 4 ohm is connected to VA. So obviously you will get 1 by 4 as its conductance. Alright, there is this J2 ohms that is connected. There is this J2 ohms that is connected to what do you call? This 2 ohm is connected to VA, not J2. 2 ohm is again connected to VA. So that will be the conductance is 1 by 2. And minus J2 is connected to VA. So minus J2 is, the susceptance is 1 by J2 with a negative sign. Okay. Rather it is plus 1 by minus J2. We can put it this way. Alright. So it is reciprocal of resistance. Reciprocal of resistance is conductance. Reciprocal of reactance is what we call as susceptance. It is indicated by B. So collectively G plus R minus JB is what we call as admittance. This is admittance, or in other words it's Y. Okay, so it is reciprocal of Y equal to 1 by Z. Alright, so when we talk about nodal equations, we try to take sum of all the admittances meeting at node A. So at node A, we have this 4 ohm, we have this minus J2, and we have this 2. So we take the reciprocal of all those things, add them up. That becomes the admittance at node A. Okay, sum of all the admittances at node A. Okay, so that we have taken, and that has to be multiplied with the node voltage VA. All right, so we have taken the sum of admittances. Now we will try to enclose it within bracket like this into VA. Okay, so here this can be, this minus here can be removed, this can be removed, and it can be put here. It would look neat. Alright, so this is my first term. Minus, there is another node, right? Minus sum of all the admittances that are common between VA and VB. What are the admittances that are common between node A and node B? Rather, VA and VB is 1, this 2 ohm is common, and minus J2 is common. So if we take that, it will be, I'll open up a bracket. This is 1 by 2 minus 1 by J2. I suppose it's clear. Okay, into VB equal to the sum of the currents entering the node, entering that respective node. We are trying to write an equation for VA. So the current that enters the node is this current, that is 25 at an angle 90. This is the current. Alright, so this is one equation we have. This equation can be further simplified using calculators. You get it as I have simplified it, 0.75 plus J 0.5 into VA minus 0.5 plus J 0.5 into VB equal to 25 at an angle 90. This is my equation 1. Alright. It is simple. How do we write the second equation? Second equation is written for node B, which has a potential of VB. The same logic we will extend. Okay. So while writing the second equation, we write this particular coefficient, now the coefficient of VA first, then VB. So what is common between VA and VB? Sum of all the admittances connected between VA and VB with a negative sign is taken first. Right? So that is equal to minus of 1 by 2 minus 1 by J2. This into VA. Okay, common between VA and VB. Right? And plus sum of all the admittances that are meeting at node B. Okay, sum of all the admittances taken at node B, that will be equal to, how many are there? So at node B, if we take 1 by 6 is there, so we will write 1 by 6. Then another resistive part we will take 1 by 2 plus 1 by 2, and then plus 1 by J2 minus 1 by J2. Okay, this whole thing into VB. This is equal to how many current sources are there? How many currents are there? Incoming current. Okay, sum of the incoming currents. So incoming current is taken a positive sign, and I will take this little on the side so that I'll get some space. Some of the currents that are entering the node. So at VB, if we look at the currents, both the currents are going away from VB. So they will have a negative sign. So the sum of the currents is minus 25 at an angle 90 is one current. That is this current source. And the other current source is minus V1 by 6. Okay, so how have we done? We will look back again. It is a simple thing. Normally, a problem of this nature, if this was not given, like 4 ohm, one end of 4 ohm resistance, you please ground it. If that is not given, we would have taken VB to be the ground and this node to be the ground, and then we would have gone ahead. It would have appeared simpler. Otherwise also it is the same thing. Here one condition is that any node can be made as the reference node. That is the emphasis that is conveyed through this problem. Okay, so we have to recollect. If you forgotten, we have to recollect the equations are of this form: y11 v1 plus y12 v2 equal to I1, y21 v1 plus y22 v2 equal to I2. This is how the nodal equations are written, where y11 is the sum of all the admittances meeting at node 1. y12 is sum of all the admittances that are common between node 1 and node 2. Similarly, y21 is the sum of all the admittances connected between node 2 and node 1. Eventually, we have observed that y12 equal to y21. This is also true. And y22 again is sum of all the admittances meeting at node 2. Right? So this is how we have understood nodal equations, and we are trying to write the nodal equations by inspection. That's what we have done. We have written both the equations. Now we will try to simplify the second equation. Now that we have written the equation, simplification wouldn't take much time. We have calculators, we have scientific calculators which will do the work for us. This will be written in this manner. With little simplification, we can arrive at the second equation. See if we can see this thing, rather this J2 will get cancelled with minus J2, and you will have 1 by 6 plus 1 by 2, that will be plus 0.67 into VB. This is equal to minus 25 at an angle 90 minus V1 by 6. Right? This is my equation 2. Now, what is the unknown? What is the unknown? See, VA and VB we don't know. At the same time, we don't even know V1. V1 is to be determined. How do we determine V1? So we have two equations, right? Two equations will give us only two unknowns. You use two equations to evaluate only two unknowns. So, however, we have V1 as another unknown. But there is another condition, circuit condition given in the problem. He says the current through 4 ohm resistor is 0. That is what he says. Where is 4 ohm resistor? We have the 4 ohm resistor placed here between the ground and node A. Okay. So what is it given? So we will write given condition is that current through 4 ohm resistor is 0. This is given. So in general, what is the current through 4 ohm resistor? If we write current through 4 ohm resistor, this is equal to VA minus 0 divided by 4. Alright. So where is 4 ohm resistor? 4 ohm resistor is connected between VA and 0. VA being higher potential and the other end is being grounded. So VA minus 0 divided by 4 will give me the current through 4 ohm resistor. And he says this current through 4 ohm resistor is 0. Alright. Or in other words, if we can cross multiply, we will see VA equal to 0. Okay, VA has to be equal to 0. How do we write the expression for VA? So using equation 1 and 2, we can apply Cramer's rule and obtain. Okay, we know how to write the Cramer's rule, right? So should I reproduce the equation? I think that would be preferable. What I do is, I will just take this one equation, I'll take it one beneath the other, copy, so that the comprehension becomes easy. Okay, this is my equation 1. Okay, I will take this equation, I'll copy this equation also, I'll put it underneath this equation. Okay, I've taken equation 1 and equation 2, kept it one underneath the other. So what is the expression for VA? We will use Cramer's rule. VA is equal to, we write the discriminant delta using the coefficients this, this, this and this. Okay, that's how we write discriminant delta in Cramer's rule. Okay, and in the delta, the first column, we replace the first column by these two quantities. That becomes VA. That is what is VA equal to. You need to look into mathematics as to how Cramer's rule is applied. Okay, this is the ratio of determinants. The first determinant is 25 at an angle 90. I can give a trivia if, people should know. Still, maybe I will give you that trivia. A side note, 0.67. This is VA divided by this determinant divided by what is called as delta. This is equal to 0. We need not write delta, basically because when cross multiplied, delta will vanish. Okay, when cross multiplied, this delta would get multiplied with 0 this way, it will be 0, right? So I will have only the determinant to be equal to 0. So what I mean is, this determinant, or else I will copy the determinant. Why should I spend time in writing the determinant if I can copy this? Copy, put it here. This determinant is equal to 0. This is equal to 0. So I can expand this. How do I expand this into this? Minus this into this will give me the value, right? I will do that simple multiplication. This is 25 at an angle 90. So you may need to know this. 25 at an angle 90. I'll put it in brackets. 0.67 minus, because this is also minus, here also I will get minus is common, minus of minus plus, and that again is minus, into 0.5 plus j 0.5 into 25 at an angle 90 plus v1 by 6 equal to 0. So this is my equation from which I will evaluate v1. It is very, very simple thing to do. Okay, so we can do this computation. We have calculators to do. Left hand side can be multiplied and you can get. However, if we do the computation, it will be, you can work out the calculator. So you will get it to be equal to 12.5 plus j 4.25 equal to 0.5 plus j 0.5 divided by 6 into V1. You can do simplification. Your calculator will easily give you. So V1, if you can compute, so you will be equal, it will be 6 into 12.5 plus j 4.25 divided by 0.5 plus j 0.5. That we will get it as 100.5 minus j 49.5, so many volts. Okay, or in terms of polar form, Therefore, V1 should be equal to, you will get it as 112.03 at an angle minus 26.22 volts which results in zero current through 4 ohm resistor. So this much voltage is needed to be applied so that there is no current in the 4 ohm resistor. This completes the problem. Alright, it is very simple. It's very simple. Now I will give you a trivia here, where I will make some space and give you some side note, like the Cramer's rule. If viewers don't remember, students who are trying to look into this problem, if they don't remember, maybe I would give small trivia to it. Some side note I'll give you as to how to apply Cramer's rule. I'll shrink it a bit, take it here. Okay, so I will okay, I'm trying to make some space. Okay, now how do we apply Cramer's rule? I'll give simple example like this. Suppose I have equation like a11x a12y equal to C1, a21x plus a22y equal to C2. These are my two simultaneous equations. Okay, so a11, a12, a21, a22, they may be complex numbers, they may be simple numbers, numerals. C1 and C2, they may be constants or they may be variables. If there are variables, they need to be evaluated, as the case here is. However, if these are the two equations, how do we find out the value of x and y? If these are the two equations, according to Cramer's rule, what we do is we will try to evaluate a discriminant delta which is equal to a11, a12, a21, a22. This discriminant delta is evaluated and x is equal to, you replace a11, a21 by c1, c2. You retain the other two as it is, divided by delta determinant. You do like this. And y is evaluated as, now we will retain a11, a21 from this delta, and a12 and a22, they get replaced by C1, C2, this again divided by delta. This is how you apply Cramer's rule. Alright, so in this problem we didn't evaluate this delta. If we wanted to evaluate delta, we should have taken this coefficient as the first element along the first row. This element should have been taken as the second element along the first row, and this coefficient is again would have come as the first element of the second row, and 0.67 would have come as the second element of the second row. Alright, that would have been delta. So we didn't evaluate delta because we know when VA is equal to 0, something upon delta when equated to 0, it gets cross multiplied and it becomes 0. There is no need for us to evaluate this delta. We don't need to write delta. That is the idea. That is the idea of not writing delta. Otherwise, if at all the right hand side of the equation had some constants, and if we were to simply evaluate VA and VB, then we would have written delta and done the problem. So I suppose this trivia, this side note of Cramer's rule would help in understanding how to solve simultaneous equations. Alright, so this is how the problem is done. So a quick recap perhaps would help in understanding the problem. So here in this particular problem, if you look at the problem, we have to, this is the unknown. The unknown is here. It is not the node voltages that we need to evaluate. It is not VA and VB we need to evaluate. So we need to find out what is the value of this V1 which would make the current in 4 ohm 0. That is the objective. Alright. So we need to remember the problem quite well, and we need to understand as to how to go about the problem. Okay. So here in this particular problem, if we can have a recap, the one end of VA is to be grounded. We could have even grounded this end, and this end could have been grounded. That end could have been grounded, and the other end could have been taken as the node. So it doesn't matter which end is grounded. So we have grounded this end of the network, and remaining nodes have been identified. There are only two nodes left, VA and VB. So we write the nodal equations by inspection. So the first equation is written for node A, whose potential is VA, and this is how we write it. These equations again is, if you remember, we write it as y11 V1 plus y12 V2 equal to I1, y21 V1 plus y22 V2 equal to I2. That is how we write the simultaneous equations for based on node voltage analysis. What is y11? Y11 is sum of all the admittances meeting at node 1. Here to this problem, it is sum of all the admittances meeting at node A, whose voltage is VA. How do we write? What are the values? It is 4 ohm is meeting here. One end of 2 ohm is also connected to VA. One end of minus J2 is connected to VA. So we have taken the sum of all the things into VA. And what is the next element? How do we write the next element? It is y12. What is y12? Sum of all the admittances common between node 1 and node 2. This suffix 1, 2 indicates that what is common between node and node 2. If we look at node 1 and node 2, in this case it is node A and node B. What is common between node A and node B? These are the two elements. Minus J2 and 2 ohm are the two things common. So we have taken the sum of that, and that has to be taken with a negative sign. This we have understood by inspection. Okay, so this element becomes negative and equal to sum of the currents meeting at node A. So the current that is meeting at node A is 20 from the source. It is 25 at an angle 90 degrees. This is the current. Similarly, the second equation is also written, and then of course solution of equation can be handled using Cramer's rule, and you have your scientific calculator which will help you do it. Right? So here in this particular problem, we didn't evaluate delta specifically because we know that VA is equal to 0 would mean the denominator when multiplied with 0 would vanish, and you will get the value of VA to be equal to 112.03 at an angle minus 26.22 volts, which is in polar form. If you want, you can convert it into rectangular form and also keep it. That will also be okay. But however, we have written the answer in polar form. I suppose this is understood. So a couple of more problems, maybe I will take it up in my future videos, and I would post it on YouTube. I would be happy to receive comments, and that'll help me incorporate the suggestions and improve the content. Thank you for viewing. See you in the next video. Maybe I'll make one more on node voltage analysis before I move on to the network theorems. Thanks for watching.